Kinetics of rigid bodies in 3 dimensions. For this one, we're going to go back and review a few things from previous chapters. So we'll start in 2D, what you're familiar with, and then expand that into 3D. There's also some moment of inertia things to try and remember back from statics. So chapter 9 in your statics book, if you still have that around, and we'll review some of those inertia concepts as well in this video. Applications of where you see this: gyroscopes, robotic arms, radio telescopes. Keep in mind that most motion, you can reorient your coordinate system, and that motion is actually contained in 2-dimensional planes. But there are quite a few applications where you get genuine 3-dimensional motions, where you have to keep track of things happening in 3 different directions for objects. Let's go back and think about our forces and moments, linear momentum, angular momentum, and what that looked like previously. So we would start out by drawing a free body diagram of our object, showing all of the forces acting on it. And dynamics versus statics, those forces and moments would not add to zero, and whatever didn't balance out, that's which way it was accelerating, or that's what was going to change how fast it was rotating. And a simple way to solve these problems, we would attach these motions to the center of the object. So this line above acceleration and moment around the center of gravity, this is the simplest way to analyze these problems, is to kind of attach everything to the center of gravity. The new thing in 3D, and I will show you why this is, before R cross mv, v is r omega, r squared m, you got these inertias, and so we would look at the inertia happening around the center of gravity. And in 3 dimensions, it's not quite that simple. So calculating the moment of inertia gets quite a bit more complicated. So let's go ahead and jump into that. We'll start with 2D again. So just a reminder of what's happening in 2D, and then we're going to expand this to 3D. So pay attention here to any time you see a moment of inertia. So 2D, here's your forces, they don't add to zero. Or if you have rotational motion going on, you would analyze that and deal with it using that moment of inertia. So again, kind of that r squared m, or if you had the radius of gyration, it made it easy. So free body diagrams. And then for our kinetic diagrams, you always had kind of these 3 things. You attach the x and y accelerations, and then this rotational motion. And you think, well, in 3D, instead of x and y, you have x, y, and z accelerations, which is true. But it's this rotational piece that's going to get a bit more complicated here. Let's start out with linear momentum, and then we're going to go on to angular momentum. Linear momentum, remember that comes from acceleration dv dt. So we're looking at impulse, FDT, changing the velocity. And this is a vector. So you would divide forces into x, y, z components, forces in the x direction, change the velocity in the x direction. Same with y direction and z direction. Okay, so adding that third direction for linear momentum, no big deal. You add everything x, y, z direction. And then this final motion, you're going to attach it to the center of gravity, very similarly to what you've always done. So if you can add vectors and break things in x, y, z components, no big deal for linear momentum. Let's go on to angular momentum. So this is where we had moments. And those moments, if you have kind of an MDT, an impulse going on that's changing the rotation of it, before that r cross mv turned into r squared m omega or I omega. This is the different part that's going to change a bit in 3 dimensions. 2 dimensions, where this I omega comes from. Let's just review that real quick because that's going to be important. So we're looking at our moment, r cross ma, and changing that rotational motion by, instead of kind of a linear impulse, it's a moment through a time that changes our rotational velocity. So r cross mv. For r cross mv, first let's look at what our velocity was. So velocity is omega cross r. And in 2 dimensions, the rotation is happening around the k direction. So we have our motion happening in x and y, and everything is confined to the x and y plane, which means it's rotating around that axis coming out of the board. And all of these zeros are going to make our velocity a much simpler quantity. So remember how to do cross products here. In the I direction, you have left times right minus right times left. So you have this ky combination. And then in the j direction, you go the opposite. So k times x minus 0. So you have that kx in the y direction, and then in the z direction, 0, 0, we end up with 0. Okay, so that is just the velocity. Now we're going to take this velocity in here and do r cross mv for our angular momentum. So here is our r cross mv, where we're substituting in this velocity we found. And if you look at what happens here, we end up with our x, we get this rx squared. We also get our y squared. And then everything else is 0. So everything here is happening in the k direction. And we have x squared plus y squared. And if you remember anything about polar coordinates or polar moment of inertia, if you add together the x and y directions, let me just draw that real quick. So if you have anything in the x direction, the y direction, what you end up with is the distance away from kind of that axis coming out of the board. So this is the distance away from your z axis. Okay, a squared plus b squared equals c squared. So that's where we got that nice inertia happening around our center of gravity. And you can combine this together and we get a very simple relationship for that r cross mv turning into our moment of inertia. Okay, so that was 2D. Keep in mind all of these zeros in the system. And we're going to go ahead and crank through this in 3D and see what happens when we no longer have zeros. So here we are in 3D. Let's start again with our velocity calculations. And this time there's no zeros in here. So we have ijk components for our rotation, and we have xyz components for our position vector. So we have j times z minus k times r. We can go through that entire cross product. So we have, here's our I components, our j components, our z components, and this is just the velocity so far, okay? So there's our velocity. Now we have to plug all of this into r cross mv to turn it into our angular momentum, okay? So r cross mv. So it's already looking a little bit uglier. Now let's go through this big, huge cross product for angular momentum. Okay, in the I direction, so remember how to do cross products. Left times right minus right times left. So here is the I direction. There's a few things here that maybe you recognize. We have a y squared, a z squared, but then we have this xy and yz combination. So you can see that y squared, and then we have this yx combination, z squared, and then we have a zx combination. Going on to the j direction, this is where you go in the opposite direction first for those cross products. So we'll crank through all of this stuff again. Here's the k direction, again, crisscross. So we have quite a lot more going on when looking at our angular momentum, r cross mv here. Does this turn into anything looking like our r squared m, our moments of inertia? Let's think back to what polar moments of inertia are. So anything that we can get x squared plus y squared equals r squared. And keep in track that x and y are going to go with something in the z direction. So we're looking at perpendicular relationships here. This is a bunch of cross products. X and y will go with z, Or if I have z and y, that would go with x. Or if I have x and z, that would go with y. So any two combinations like this that you see, just figure out what is in that third direction that's perpendicular, and you can kind of add together these squared components here. Okay, so what squared components? So if I have y squared and z squared, that we can add together. Or if I have x squared and z squared, those I can add together. X squared and y squared, these I will add together. So there's a few things in here that we can start grouping and simplifying our system with. For the x direction, if we combine that y and z component, these guys are going to turn into our inertia in the x direction. Now we still have this xy and zx combinations. These are products of inertia, and I'll go through what those are in a second. There's some scenarios where these actually go to 0, and that's how we're really going to try and simplify these systems. But for now, let's keep track of this y squared z squared goes to ix. So now we're getting back into looking at some inertias that you can recognize. So cross products here. So hx, I'm going to have inertia in the x direction, and then I have these products of inertia, y, inertia in the y direction, z, inertia in the z direction. So I'm starting to see a few things that look somewhat familiar here, which is great news. Inertia around the x direction, y direction, z direction. So remember, if you'd look up the moment of inertia of objects in a table, and you would get something like this, where you had some three-dimensional object, it had axes, x, y, z, and then you had to try and figure out, so like if I have an equation ix, that would be how hard is it to rotate that object around the x-axis, or if I was going around the z-axis, there's a different equation, and it looks like y-axis has a similar equation. Okay, so that would be these ix, iy, iz, and notice the bar above the top. These are being taken with respect to the center of gravity. There might be another table that would take it around the end instead of the center of the thing or something. Okay, what are these products of inertia though, and where did those come from? This is around the x, y, z direction. What if we wanted to rotate our object around some other crazy orientation? Not x, not y, not z, some other random orientation. And we'll talk about how to do that. And also, the most important question here is what axis is the hardest to rotate around and what axis is the easiest to rotate around? So that has implications for energy efficiency or stability of an object, and things that really want to rotate around the direction that's easiest for them. So this is going to get into these IXY, IXZ products of inertia. I'm going to jump back into statics and a 2D, and let's go back and talk about product of inertia. So this isn't R squared A or R squared M. It's the direction in the x, direction in y, x times y times dA in 2D or dm in 3D. This is called the product of inertia, and we're going to use it to find our principal axes of inertia and to translate between rotating around different axes here. Okay, so if we're dealing with an axis of symmetry, and this is very important, so let's say if I go up around x, I have this direction y, down is negative y. When I add all these together, we're integrating here. So if you add everything above and below and it cancels out, great, our product of inertia is 0. So look for symmetry, but this doesn't always happen. But if you can get an axis of symmetry, that very much simplifies it. You get a bunch of zeros here. For the parallel axis theorem, it works the same way. So a bar above it, that is the product of inertia around the center of mass. And if we're trying to get that around some new axis that does not go through the center of mass, it's going to be larger. And the farther away we get, so this x bar, y bar, that is the distance from the new coordinate system to where your center of mass is. So here's the center, here's X bar, here's Y bar. So as you get farther and farther away from your centroid, your inertia gets larger and larger. It gets harder and harder to rotate this thing. Translating between one axis to a new axis, and this is really where the product of inertia comes into play. So let's say we know the inertia around this black axis, but we want to figure out the inertia around this red axis. If you try and get coordinates with this new red orientation as a function of this black orientation, okay? So I have, if I look at this red dot, okay, I come over X and then I go up Y. That's the coordinates according to the black coordinate system, X, Y. If I want to describe that red dot in terms of the rotated red coordinate system, so I'm coming up, up, up. What I can do is I can say, oh, this little chunk is X cosine theta. So here's our old X, here's theta, it's adjacent side. Okay, so this chunk is X cosine theta. This angle ends up translating over here. This little piece is Y sine theta. So if I add X cosine plus X sine, then I can get this new length along the red coordinate system up to this. Okay, so you can get the new coordinate in terms of the old coordinates. And you can crank through some calculations to see what the moment of inertia is with respect to the new axes if you know what it is to the old axes. And I won't go through this entire derivation. This is from your statics book. You'll see it in Mechanics of Materials. The long and the short of it is going back and forth between these two coordinate systems. You end up with a circular relationship. It's very interesting. So kind of an a squared plus b squared equals c squared sort of a deal. And you can relate how hard it is to rotate around any new axes if you know what it is around some original coordinate system. Okay, so keeping track of this equation, so we're going to look at kind of the average, which is between Ix and Iy divided by 2, the average of those two directions. And we're also going to be using this Ixy product of inertia concept too to do this. For this, we're going to use something called Mohr's circle. And if you plot out the product of inertia, Ixy, with respect to Ix and Iy, every point along this circle describes the inertia for a differently oriented coordinate system, where the radius of that circle you can get by looking at the average between Ix and Iy, and then it's kind of an a squared plus b squared equals c squared deal. So we're looking at the product of inertia in Ix and Iy. Let me go ahead and walk through an example for this, and hopefully you have this in fast forward mode, but I think it's really important to understand, especially if you're going on to a mechanics and materials class, because you'll see this again, and inertia is extremely important again for energy efficiency and stability. So this is an important concept that you'll see over and over again. Okay, so here's an object, and let's say we want to figure out the principal moments of inertia. We want to figure out what axis is easiest to rotate around and what axis is hardest to rotate around. And right now we have this black coordinate system, right? And we can figure out what the inertia is around this black coordinate system. In fact, they give us Ix and Iy, and that is with respect to this coordinate system shown. But it doesn't look like that's going to be the easiest or the hardest to rotate around. In fact, remember, inertia is that r squared m. It's highly dependent on r. You can think of like an ice skater pulling her arms in. So the easiest coordinate system to rotate around, if I draw a line through here where the mass is really hugged up against it, right? So this is going to be the easiest. And if I draw a line perpendicular to that, this would be the hardest to rotate around. So that's what we want here. We want the principal axes of rotation, and we want to know from where we are to the new coordinate system, how much would we have to rotate this around to figure out where those principal axes of rotation, principal moments of inertia are. Okay, we're going to do that with a Mohr circle and also using the inertia around this original coordinate system. So we're going to need two things. We need Ix, Iy. We also need our product of inertia. So instead of x squared a or y squared a, it is x times y times a. Notice for the center chunk, if it's symmetrical around the axis, you get zeros, so we can calculate the product of inertia. Now we have three pieces of information that is needed to draw a Mohr circle and find the principal axes here. We are going to put our product of inertia around the y-axis and Ix and Iy along here on the x-axis. So the first line we're going to make is, here is our Iy, okay? We're going to just plot this like xy. So this point is made from, on the x-axis is going to be Iy, and on the y-axis is our product of inertia. For the other point, so right here, this is again product of inertia, which is over here. We have one side that's positive and one side we're making negative. And then we're also plotting the inertia around the x-axis here. So these initial points represent the inertia around the initial axes over here. We then want to rotate this around, and what we're after is the maximum and the minimum. So we want to try and find this new red point, which means we're going to try and find this angle. Keep in mind that the angle here is 2 times the angle that will be actually rotating our coordinate system over here. We can find the center of the circle just by finding the average between Ix and Iy. We can get the radius of this circle with just some trig here. So we're looking at the height is that product of inertia. So the average plus the Ixy squared, a squared plus b squared is equal to the radius. Once we have the radius, we can see what this angle is, and then we can find this min and this max. So this is where we're going to just rotate this entire coordinate system by this angle, and we can find the new principal moments of inertia. Okay, so that's the long and the short of the point of Ixy, the products of inertia. It doesn't really have a physical significance. It's more of a mathematical tool in order to construct this Mohr circle and find the principal moments of inertia, or the axes that the object wants to rotate around. Okay, so that's a little bit of background back from statics, and something that you'll probably do a lot more with in mechanics of materials. So you can say, oh, Ix and Iy was 10 and 6.97. That was around this black axis. And if you look at the new one, the minimum 1.89. So look at how much smaller that is than 6.97. So very small, and 90 degrees to that, 15, very large. So we have A is a very large, and then B is this very small one. That's where everything is really wrapped around that axis. So be familiar with those terms, what the product of inertia is, what the principal axes of rotation are. Let's go through a three-dimensional concept question out of chapter 17. So what we have, and this is an instantaneous solution. So the next instant in time, it'll have a whole different thing, but we're just going to take this one instant at a time. So at the instant shown, the disk rotates with an angular velocity omega 2. So let's find omega 2 over here. So it looks like this disk, it's kind of spinning around point C. So there's one type of motion going on. So it has an angular velocity omega 2 with respect to arm ABC. Yeah, so it's spinning around this point C. And this arm is rotating around the y-axis with omega 1. So, okay, omega 1, this is what's going to turn it into a three-dimensional problem here. We don't have just rotation around one direction. We have there's two different directions of rotation going on here. Find the directions of the angular momentum. So here's angular momentum, r cross mv, that's all of this, ix omega x, ix y, products of inertia. Okay, figure out the angular momentum of the disk around point A. Where is point A? Here's point A. Okay, so we're not getting around point C, which would be the center of mass. That would be the easiest point. We're trying to figure out angular momentum around point A, way down here. A couple different things we're going to do. Let's start by figuring out what the angular momentum is around the center of gravity. So H around C happens to be the center of gravity here. So HC or HG, and that's going to be this whole thing. If we're looking at the disk, this is symmetrical. And what that is going to do for us is we can get rid of all of these products of inertia. So because it's symmetrical, we won't have to worry about any of these xz, xy. Those are all going to go to zeros. And the main thing we're interested in here is these inertias around the center. So we have a nice symmetrical object, and we can look up the ix, iy, iz for this disk. So we're only worried about the angular momentum of the disk here, not the arm, not everything else. It's additive, so if we wanted some other pieces to it, we could do that, but we're just worried about the angular momentum of this disk, and we're going to first figure out what it is around the center, but then we don't want it around the center, we want it around point A. Okay, so if I get it around point A instead of the center, that means I'm going to have to add this other chunk to it, r cross mv. So that comes from like the parallel axis theorem. So let's go ahead and concentrate on this yellow chunk of it first and get ix, wx, iy, wy, iz, wz. If we add up all of our angular velocities, what directions are those in? So here is my z direction. And if you look over here at omega 2, it is spinning around the z direction. Okay, so we have omega 2 in the z direction. And then omega 1, what direction is it in? So here is the y direction. And you see how omega 1 here is in the y direction. There is no rotation in the x direction, so we can get rid of this term. And the two things we're going to concentrate on here for omega x are y and z. We can go to the tables and we can look up the moment of inertia for a disk. And since we're not worried about the x direction, we just have that rotation around the y and the z directions here. So then we can look up the inertia around the z direction, and the inertia, it looks like it's symmetrical, so it doesn't matter if you're talking about y or z here, but we can figure out what those inertias are, and we can figure out what omega is, and we can get, so that is this very first part of the puzzle, okay? And it wanted us to know like just the direction of the thing. So let's pay attention to the directions here. So we have something positive in the J direction going on and something positive in the K direction going on for this very first part of the puzzle. So this is the angular momentum around the center of mass, and that's going to be part of it. Now let's go on to this next chunk, which we're going to have to use this R cross MV cross product in order to switch it down so we have the angular momentum around this point A instead. Okay, so we're going to be doing R cross MV. So here's from the new axis of rotation to the centroid. There's our position vector. So we're going over 18 and up 9. And then the velocity of the center of this thing, it's kind of like going around in a circle, right? So you have R cross V, where V equals R. It's whipping around this y-axis, so it's going to have kind of a velocity in this negative z direction. Can you kind of think about how it's moving and see how this entire disk at this instant, this is an instantaneous thing, it's going backwards in the z direction. And we can go ahead and walk through that cross product here. So here's our position vector, right? R to C. Here's our velocity, so omega cross R, and we see that the velocity of the center of C is going backwards in that z direction. This is the z direction. Okay, so for this last little piece of it, so here's our R cross MV. There's our V is going back into the board. And for this piece of it, we end up with a negative I component and a positive J component. So putting everything together, we have what the center of mass was doing. So that had a positive J component and a positive K component. And then for this green chunk of it, that's going to get us over to A, right? Then we have negative I, positive J. So if you put all those together, you end up with, we have our negative I. Okay, so here's this piece of it. So we have negative I, that gives us this. And then for the rest of it, okay, this is this piece of it. We had a plus J, and this was also plus J, so we can have a plus Y, and then here's our plus K, plus K. Whew, that was quite the thing to get through. Okay, but hopefully you get the point. So if we have the angular momentum around some new point, we can grab it around the center of gravity and R cross MV, add that to it. Just pray that you have something that's symmetrical so you don't have to worry about any of those IXY product of inertias, because that's where these problems start getting really hairy, and you could do it if you had enough time. It just take a lot of sitting there staring at it for those ones. Okay, so that was angular momentum, R cross MV. What about work energy? What does that look like in 2D versus 3D? So let's start with 2D again. Work energy. This is where instead of looking at velocity changing with time, we use this little chain rule. dSdt goes to V, and this lets us look at forces acting through a distance changing the kinetic energy. So instead of impulse, FTT, we're looking at FPS, force through a distance, and this will change our energy. This turns into 1/2 mv squared. And FTS, this could be considered work, or it could be mgh. kx dx 1/2 kx squared. This could be potential energy or work, but we're looking at changing the velocities. In 2D, if we had translational and rotational motion, there's two pieces to that velocity. There's the center of mass, the velocity of the center of mass of the object, and then if it's also rotating, the velocity of every little point on that object is going to be a combination of what the center is doing and the motion with respect to the center. So you're going to be adding together these two pieces. So we have v plus omega cross v, and those two together give the total velocity of each little part of it. And then when we have this omega cross r squared, we get this r squared m, and that turned into inertias. Okay, so 2D versus 3D. Remember all of this stuff for 2D. And in 2D, this really is the equation you want to start off with. So translational and rotational energy, that would be changed by FDS work, or if you have a moment acting through an angle. So moments would change the rotational energy of it versus FDS would change the translational energy of it. So this little equation gets expanded quite a lot if you're looking at translational and rotational motion. Just like before, it's not going to be as easy in 3D as it was in 2D. So in 2D, we could just slap this moment of inertia in there and we were good to go. For 3D, we're going to do the same thing for energy that we did for angular momentum. When we add up the velocity of each piece of that object, and that turns into a huge integration, and we end up with products of inertia again, as well as Ix, Iy, and Iz. Now, if we have something rotating around the principal axis, then we can get rid of all of these products of inertia, and it's simplified to Ix, Iy, Iz. So 2D versus 3D, and I'm not going to give you anything too horrible with these products of inertia, but know they exist, and we will do the easier situations where we're rotating around something that goes through the center of mass that has some axis of symmetry, so we won't have to worry about these products. And we're just adding together the Ix, Iy, and Iz, versus in 2D, it was really just this Iz that we were worried about in 2 dimensions. Okay, so that's the 3D version of kinetic energy. And then for the work and moment and everything else, again, you're going to split force into XYZ components. Make sure work, that's a dot product. So you're looking at the X component of the force and the X displacement and Y with Y. So everything else is the same. It's just this inertia that we're going to be adding some additional terms into if we have some three-dimensional motion. Okay, here's another concept question. So we have the same setup that we had before. The disk is rotating with angular velocity omega 2 with respect to the arm ABC. So we have this omega 2 in the z direction. And we also have omega 1, that the whole thing is kind of swinging around this y-axis. What terms will contribute to the kinetic energy of the disk? So we have a bunch of stuff down here. Which ones would go into our kinetic energy? So again, our kinetic energy is what the center of the thing is doing. And now we have Ix omega x squared, Iy omega y squared, Iz omega z squared. So what is x, y, and z versus 1 and 2? Let's go ahead and draw on this a little bit. Okay, so what direction is omega 1 in? We have omega 1 is wrapped around the y-axis. So right here, this omega y, this is going to be omega 1. So Iy goes with omega 1. So we can circle this one. That's going to be this term right here. And then here, let me grab a different color here. for our omega 2, what direction is omega 2 going in? And it looks like omega 2, this is the z direction. So if we're coming right out of here, so we're wrapping around in the z direction here. So omega z, this is omega 2. So if we look for this combination down here, iz omega 2, that's going to be this term right here. And then we don't have anything in the x direction, so I can get rid of this. Between what's left, so let's see, z went with 2, not with 1. And we still need to figure out what this last term is doing. So what is the velocity of c? Well, there's going to be some lever arm, right? And then we're rotating around it, so the velocity is going to be some kind of a r omega or l omega. So here's our, if we do velocity squared, that's going to be L squared omega squared. So there's our three terms that are going to go into calculating the kinetic energy of this thing. So we have J and K components, no X components, and our center is omega cross R. So there we go.